Whew. I'm thinking I should just dive right into wow. So it's 2 hours is pretty long for a stream for me, but I do want to get day 19 done. So maybe day 19 will be faster. He says, hopefully. Based on the length of this, the answer is no, it will not be faster. Holy crap. All right. We can do this. We can do this. Beacon scanner. As your probe drifted down through this area, it released an assortment of beacons and scanners into the water. It's difficult to navigate in pitch black open waters of the ocean trench, but if you can build a map of the trench using data from the scanners, you should be able to safely reach the bottom. Beacons and scanners float motionless in the water. They're designed to maintain the same position for long periods of time. Each scanner is capable of detecting all beacons in a large cube centered on the scanner. I'm going to pass over the cube versus centering because it should be a sphere, right? Beacons that are at most 1,000 units away from the scanner in each of the 3 axes have their precise position determined relative to the scanner. However, scanners cannot detect other scanners. The submarine has automatically summarized the relative positions of beacons detected by each scanner, your puzzle input. For example, if scanner is at XYZ coordinates 500, 0, negative 500, and there are beacons at negative 500, 1,000, negative 1,500, blah, 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 the scanner should report the first beacon is at negative 1,000, 1,000, negative 1,000 relative to the scanner, but that would not detect the second beacon at all. I'm going to pretend I understand that and just keep going. Unfortunately, while each scanner can report the positions of all detected beacons relative to itself, Shrishak says, yeah, I thought it would be sphere. I don't know why it's mentioning a cube. Yeah, I think it's just because it's easier to think about cubes. the math becomes a lot simpler. Scanners do not know their own position. You'll need to determine the positions of the beacons and scanners yourself. Scanners and beacons map a single contiguous 3D region. This region can be reconstructed by finding pairs of scanners that have overlapping detection regions, such that there are at least 12 beacons that both scanners detect within the overlap. By establishing 12 common beacons, you can precisely determine where the scanners are relative to each other, allowing you to reconstruct the beacon map one scanner at a time. All right, that seems key. Being able to do it one at a time is key. Because I was just thinking that, well, what if there's scanners in different groups and subgroups would map to each other, and then you'd have to have like a super group that would. But if we can do it one at a time, that's handy. All right, this is a 2D example. Unfortunately, there's a second problem. The scanners also don't know their rotation or facing direction. Due to magnetic alignment, each scanner is rotated some integer number of 90-degree turns all around the X, Y, and Z axes. That is, one scanner might call direction positive X, while another scanner might call that direction negative Y. Or 2 scanners might agree on which direction is positive X, but one scanner might be upside down from the perspective of the other scanner. In total, each scanner could be in any of 24 different orientations. 24, right? Because we're talking about a 6-sided cube, and each cube can rotate, each cube face can rotate in 4 different directions. 6 times 4, 24. Makes sense. Okay, I think I understand that. For example, here's an arrangement of beacons. It's seen from a scanner in the same position but in different orientations. So scanner 0 can look at something this way, but if it was oriented differently, it could look at things this way, or this way, or this way, or this way. By finding pairs of scanners that both see at least 24 of the same beacons, you can assemble the entire map. For example, consider the following report. This is going to be my test input, isn't it? Test 1 day 19.txt. Okay. Because all coordinates are relative in this example, all absolute positions will be expressed relative to scanner 0. Okay. So then we do some math and we get this. So scanner 4 is at these coordinates relative to scanner 0. Following this process, scanner 2 must be at these coordinates, and scanner 3 must be at these coordinates. So we do one scanner at a time. We found 0 and 4, then we added in 2, and then we added in 3. Oh, you did 1 first. 1, then 4, then 2, then 3. Okay. And this is the full list of beacons relative to scanner 0. In total, there are 79 beacons. Assemble the full map of beacons. How many beacons are there? Easy peasy lemon squeezy. Okay, how do we want to represent this? We're trying to map things together and see which items map together in which orientation. I think maybe we want to start out with a hash set. But first we have to set up our quick fix list. Mod day 19. And then we're going to switch our second pair of day 18s to 19. And watch it fail. Good. Okay, and we run, and we see day 19. Yes, okay. So, how do we want to represent this? I think the easiest thing to do would be to create a type. Oh, we do need to be able to read in the file. I'll do that in a bit. I want to create a tuple with 3 I64s, and I just want to call it a scanner. Scan data, because a scanner is a collection of scan data, right? Oh, it's just, let's see, I64, I64, I64. And then scanner is just a vec of scan data. Yeah? And then what we'll do is we'll just read in all of our scan data. Yep, I think we need to do that right now with the test input. Create utils, read file. Let lines equals read file inputs test 1 day 19.rs. Println lines len. Okay, make sure that works. And it failed. Did I just call it test? Nope. Still can't find it. Yeah, test 1 day 19.text. What did I do wrong? Oh, .rs. Okay. That checks. We got to run 136 lines. All right, that sounds reasonable. At least we were able to read the file. Okay, so now what we want to do is process the file. We want to convert this into data. So we can say for L in lines. If L dot starts with dash dash dash, then we'll just continue. If L is empty, then we've hit a blank line here, and we can just push all of our data. Otherwise, it's going to be a triple. Let mut splitter equals L dot split on comma. Let x, which is going to be I64, is splitter next unwrap parse unwrap x, y, and z. And we will say we're going to need a full list of scan data. Oh, I'm trying to think. Maybe we don't. Maybe what we want. Yeah. Maybe we want a hash map here of scan data. Because if we can compare, like we generate not a hash map, a hash set. And that way we can do like an intersection and say, does the intersection have at least 12 points that are in common? Yeah. So that's going to be our scanner, and then we'll just say we have a scan list of scanners. Vec new, and then we're going to say new scanner. We'll just say scanner is hash map hash set of scan data. Scanner. There we go. New, like that. And then scanner insert XYZ. And here's our push data, so scanners.push scanner. And then we're going to create a new one, scanner equals hash set new. And then at the end, we have a hash set that we still need to push, scanners.push scanner. Okay, so at this point, we should have all of these scanners. There's 5 of them. Right, so we should be able to now just push, print this in a debug format and see if we got scanners. It checks, and it fails. What do I do? I don't want this anymore. Result unwrap, empty. And that's going to be on line 23. Huh. All right, let's just print this out. Oh, I hit a blank line. So it shouldn't have, oh, continue. Yeah. That's an obvious error. Okay, so we got some data. This one's this one ends in 808, 476, 593. Oh, yeah, these are not in any order. We should be able to find 808, there it is, 476, 593. Okay. And then if we look at the top, we should be able to find 876, 649. Yeah, okay. And there's 2 of them because that was the output. Okay, good. All right, so we're now able to read in our scanners. And now what we want to do is we want to grab the first one and check all of the rest of the scanners, rotating them as necessary to see if there is an offset that can be applied to one of the rest of the scanners that would allow it to align with our current scanner. Yikes. Okay. So what we need is a function called, I don't know, accumulate. And it's going to take, you know what? We had so much fun with the vec deck. I'm going to use the same thing here. and change this to a vecdeck. Because that way I can just pop off. I'll say list of scanner. And then that's all we need. And what do we need to return is just a scanner. Right? We're going to be returning just everything. Oh no, we're going to return a list of all the scanners. Right? We're going to be yeah, so we're going to return a list of all the scanners after we've processed them. And that way we can commonalize all the points in a nice little hash set. And we're good to go. Okay. So we know we're basing everything off of scanner 0. So we're going to assume scanner 0 is already in location. So we'll call this known. And we can just say known push, sure, list.pop front dot unwrap. So now we're going to base everything off of this known So we're going to say while our list is not empty, we want to find let's see. Yeah, we're going to pop one off and we're going to have to rotate it into position and compare it against all the entries that are in the known list. So we can say for check in list iter mute, so this has to be mutable, enumerate, because we want to be able to remove it if we find it, right? Once we find it in the list, we need to be able to take it out of the list. And then for k in known, if let sum offset is rotate and compare, and we're going to get back, we're going to compare it to the known one and our mutable one. We're going to mutate it in order to put it in position. Then we need to save it. So we're going to say rotate and compare will return an offset if it finds something and none if it doesn't find anything. But check will be modified to be in the location it needs to be. So we can say found is equal to some check because we're going to do this up here. Wrong window. And do this up here. We'll say let found is none. Oh, and then we need to save the index. IDX is E. And then we want to break outer. Okay. So at this point, if second is none, then the current entry in the list, oh, no, it means we couldn't find anything to merge. So we just do that. If we did find it, let's unwrap it. And we want to add it to our, oh, we might have to clone it, right? Because we want to add it to our known list now. What am I saying second? Found. Okay, I'm going, I've been streaming too long. My brain is not working. Found.unwrap, push found. I was thinking, you know, we had the first one in the knowns and the second one was the one we found, but I forgot that I call it found. Okay. And then we want, and this is where we want to remove from our list, remove IDX, because now it's no longer, we no longer have to search for it, we found the location for it. And then we're done. And then we just return the solved, the known locations. All right. I have no idea if this will work. What we need to do now is figure out how to write the rotate and compare. So this will take the known, which is going to be a type scanner. Right, we're only putting the scanners in this vector. Let's just make sure that that's explicit here. And then we have the check guy, which is going to be a scanner also. And it's going to return an option, right? We said we can either return the offset, which is going to be scan, what did I call it? Scan data. Oops, and of course I messed up the syntax on that. That's okay. So what we need to do now is figure out how we're going to rotate this. So let's think about just looking at it face on. I'm just imagining how to rotate it. If we want to rotate it at the top face, that's around the y-axis. So rotate around y. And what do we have to change? Well, first what we want to do is we're going to loop over each of the rotations. And I'll add the remaining rotations in a bit. They just need to get nested, I think. And then we want to call a function and say, are we currently aligned? Do we meet some sort of alignment? And that'll be an offset that comes back from a new function we're going to write called alignment. And this will be the known value and the check. If that's the case, then we're going to update check with offset and return offset. Okay, and I'll think about how to do that in a second. If we didn't, then we want to rotate once around the y-axis. So this will be in check. Oh, but this is a hash set. And I want to be able to do it in place. So we're going to make a backup of this thing. All right, and then we're going to modify, that's what we're going to do, is we're going to use this instead. Because that way I can just update it in place. I can just say point equals, and then rotating around the y-axis. How do we do that? Rotate on y, and that's going to be x. Just thinking, I'm trying to visualize it in my head. X becomes negative z, and z becomes x. So that should just be point.2, point.1, and negative point.0 from negative 0, from negative z. So this loop should rotate everything around the y-axis. And it checks on each rotation, it checks. And now what are we going to do here? Let's think about if B now has an alignment. We want to update check. So we can say check.clear. And then for point in B, check insert a point. Oh, plus the offset. So it's 0.0 plus offset 0. 0.1 plus offset 1. Yeah, Trishak, it says this problem looks hard. This problem is extremely hard, and it's right after another extremely hard problem. So my brain is going into meltdown mode. Offset 2. All right. So this now updates this check with the alignment such that it's now matching a known value, and then we just return offset. Okay, so that wasn't too bad. What we need to do now is rotating around the y-axis here. We want to rotate around, I don't know, let's say the z-axis. This is going to be really slow, isn't it? It's probably going to be the slowest one yet. So if we rotated around y 4 times and we couldn't find it, we're going to rotate once around z and then try again. So how do we rotate around z? Rotate around z. X becomes, let's see, it becomes negative y, and y becomes x. And that rotates around z. Oh, we don't want a point in check. We want a point in B. Right? Because that's what we're modifying. And the point is, this is 0.1, because x becomes negative y, so negative 0.0, and then 0.2. Okay. And then we still have, so those are the 4 faces around the z-axis, and we're checking around y. Now we need to check the front face and the back face. So we need to indent one more level. For x in 0.2, because we're only doing 2 now, the front face and the back face. If we failed to match any of those 4 faces, then we're going to rotate it front ways. Yeah, so if x is 0, rotate top to the front. And that'll just be for point in B. Oh, we need to do iter mutes. B dot iter mute, right? Because we're modifying the values here. Point in equals, and it's just 0.0. This becomes negative z, and this becomes y. Else, rotate twice on x, because we rotated the front, and now, which was the top, and now we want to check the bottom, which is now the back. So we need to rotate twice on the x-axis. So how do we do that? In b.iter mute, and point equals, let's think about this. X offset doesn't change. Y becomes rotating it twice. So if we go down and... Oh, okay. So it's just negative y and then z is negative z. Okay. And then if it can't find anything, it just returns none. So let's rotate and compare. Now all we have to do is write this. We keep kicking the can down the road here. So how do we do an alignment? What we need to do is loop over the known scanner. And this is now a vec of scan data. And it's going to return an option of scan data, right? Which is the offset that we're going to apply to the check. So we say for point in known, for point in check, we now calculate the deltas for each one. Point in known minus point in check. And then this is y and z. And this is 2 and 1 and 1 and 2. So these are all the deltas. And now we want to say we have to check again in check. But now we have to check every point, right? Oh, this is n cubed. This is going to be even slower than I thought. If known contains oh, I don't want to reuse PC. Let's just call it point here. Point 0 plus dx, point 1 plus dy, and point 2 plus dz, then count plus equals 1. Right? We're trying to count up to 12. So we need a counter start at 0, and then if count is greater than or equal to 12, then return sum dx, dy, dz. And then otherwise return none. And I haven't done a cargo check in a while, so I'm going to run into a whole bunch of problems. Oh, vecdec. Push back. Push back. Expected reference. That's easy to fix. We have 5 warnings, probably because we're not calling any of this code we wrote. Let us see. So we can actually call accumulate on our scanners list. And it's going to return a vector of scanners. And so I'll just print that out and see what happens. Let's see if this even runs. Oh. I'm running it here in case it's an infinite loop. Oh, wow. I got something. It took a long time, but I got something. Oh, I'm not returning the offset? I thought I need to return the offset. Oops. First D19 mod. I thought I was returning the offset. I must have. Oh. Oh, we don't need the offset. We don't care. We just care if it's sum. So we don't even have to do this. Okay. But I got some output. Now what am I supposed to do with the output again? Oh, how many beacons are there? Is that just the length of this thing? Is that just the length of this thing? It's not fast, and this is with the test input. 5. Okay. That's not what I was hoping to see. So we're returning a vector of scanners. Oh, there's only 5 in there. Right. What we need to do now is for each scanner, we need to accumulate the data. Well, we've accumulated vec, so that's not really true. This is, yeah, it is a vec. For v in vec, we're going to create a hash map. I'll call it hash set. I'm going to call it hash set because new, and then we can just say hs dot. Can we do that? Hs extend v? I don't know. Okay, and this is just HS len. Okay, that's that problem. That's that. And this is a scanner. Right? Yeah, it's just a hash set of scan data. And then we're printing out the hash set length. Let's run it. Hit test. Oh, I forgot to functions used as test can't have any arguments. Oops. Okay, I'll have to fix that. But that's yesterday's day. This is not fast. Oh, did I just get 79? I did. It's very slow though. I want to print out as I accumulate things. I want to say I found one, how many there are left. Println left to go. List.len. And then what I'm going to do is I'm going to get out of here and run it in release mode. RELEASE. Okay. So it was 203 milliseconds. Let's change our test to input. Shrishak says, apparently today's puzzle is easier to you as it took you only 30 minutes for part 1. Well, I don't know. Maybe I'm just on a roll. I got really lucky that this thing worked. Quit. Okay, let's try to run it this way. I forgot to look how many scanners there were in the input. Oh, I never saved the input. That's why I never looked. Okay, how many scanners are there? There's 0 through 34. It's 35 scanners total. Okay. Day 19.text. Close that little guy. Close the big guy. Move. Downloads. Input day 19.text into inputs. And then it will run release. Oh, wow. This is wicked slow. Yikes. I don't have that much CPU either with all the OBS and Pretzel and loopback running. And this may take a while. So how's it going, everybody? How's your day? My day's going great. CH top, it's a single threaded, so no problem. Oh yeah, I can run top. We've got 434. I do not believe that. I do not believe that. Wow, that is the right answer. Okay, but it is wicked slow. In release mode, it took 50 seconds to figure that out. Shrishak says, yay! Yay indeed. I don't want to look at part 2. What do we have here? All right. Get commit -m day 19 part 1 push. All right, dare I look? Oops, jobs. Oh, I left the O on there. Dang it. There. Okay. So I'm gonna take a look. How bad is it? Oh, this is short. Sometimes it's a good idea to appreciate just how big the ocean is. Using the Manhattan distance, how far apart do the scanners get? In the above examples, scanners 2 and 3 are the largest Manhattan distance apart. In total, they are 3621. All right, let's switch back to our test input. I called it test 1, but there's only that one test. So what do we need to save then? Right, as we accumulate. All right, so I'm going to change this back then, because what we need to do is save all the offsets that we needed to shift by. So I'm switching this back to let some offset, and then what we can do is just save them all. Right? And then when we find one, we could just say offsets.push offset. And then we can return it. So it's going to be a vec scanner and for part 1 and a vec of scan data for part 2. And down here, we just say known and offsets. And then up here, we say part 1 and part 2 are those. And this becomes part 1. Now we have to do all the Manhattan distances for part 2 between each pair of points. For I in 0 dot dot p2 dot len minus 1. For j in I plus 1 to p2 dot len. Now we need to calculate the Manhattan distance and get the highest one. Let's do this highest again. Let dist is equal to p2 of I dot 0 minus p2 of j dot 0 dot abs, and we got to put an open, right? So I'm just going to repeat that for 1 and 2. And then add them up. And then just say highest is highest max dist. And then, oh, I forgot to put the part 1 thing here. Day 19, part 1. And then day 19, part 2 is going to be highest. All right, and we're going to run this with the test data first. Right, that's what I put up there. Test 1, okay. So let's run that and see if we get 3621. All right, this is non-debug, so it's going to be slower. We did get 3621. So now we have to rerun that really long test. Oh, I got to fix my input. Hopefully it won't be that much longer, because all we're doing is saving things into a stack, essentially, a vector, and then looping over that. I wonder what can we do to speed this up? I thought I was doing it a fast way by using hash sets, and then I didn't do the intersection to do the hash sets. So yeah, time to chat with viewers. Yeah. So my day's going great, like I said before. Just the sun's out. It's not cloudy. Actually, I live in the Northeast. We had a storm come through last night. It was kind of slick rain and snow mix, but it was fine. We didn't lose power. It's probably too many for loops. Yeah, there's way too many for loops. I'm probably doing overkill somewhere. Maybe I'm doing multiple checks and stuff like that. I mean, I'm going to check this in, but there's a lot of area for improvement, I bet. All right. What do we got? We got the right answer. Perfect. All right. Let's check in with Clippy. That doesn't need to be that and that. Oh, yeah. Clippy really likes that. So on 60, we don't need the ampersand in that. And then 121, we just change this to an array, or a slice rather. Shrishak says, congrats. Thank you, Shrishak. I appreciate that. This was my longest ever stream. I've never streamed from more than 2 hours before, and my voice is really going. Git status, git commit, no, add source, git commit -m, day 19 part 2, git push. And then let's take a look at my Uncle Scientist. I'll paste this link to this in the repo if people want to take a look and give me any ideas for figuring out how to speed that up, because that is very slow. 50 seconds in release compilation. Anyway, I'm going to wrap it up because my brain is gone. And I am going to see if there's anybody around to raid Prime. Let's go raid Prime. I bet you he's having fun. I don't know what he's working on. Debugging in Rust is what it says. The Primogen. Where is he? There he is. You're welcome, Shushak. Thank you for hanging out with me. Oh yeah, he's doing AOC too. Yeah, let's go raid him. That'll be fun. All right, thanks for hanging out with me, everyone, and hope you have a great rest of your weekend. And I will see you tomorrow morning for Advent of Code Day 20. Take care.